right. So today we are going to be doing 6-4, which is going to be transformations on functions. So a lot of these operations you've already seen in the past, but you're going to see them kind of in a different way, with different notation. That's the word I'm looking for. So you may see notation like this, notation of adding functions, subtracting functions, multiplication, division, and evaluation. So I just want to clear up what this looks like, because for some people you see this and you think it's like distribution, like it's multiplying by the x, but it's actually a notation. So if it ever says f plus g of x, that really just means you're going to add the function f of x plus the function g of x. So when you add two functions, you just combine like terms. And of course, subtraction is going to be a similar scenario. You're going to have f of x minus g of x. Just be mindful of doing that because you have to make sure you distribute that negative. And next we have multiplication. That's just going to be where you multiply the f of x function times the g of x function. Yes?
If the g was first in the parentheses, would it be g minus with the g of x minus?
Exactly. Yes, good question. So subtraction and division, as we know, are not commutative properties. So it does matter the order. So whatever one is going to be on the top is the one that's going to come first in division, and subtraction as well. So good question. Yes, it could be the other way around. And then division would be f of x divided by g of x. And then lastly, this is just the substitution property. So substitution is just where you replace all of the variables by another variable that's given to you or a number. So sometimes you're going to have a conjunction or a combination of these different operations in one. So they may ask you to add two functions together and then plug in one. So that can happen. The first one we're going to look at, it gives us the value for f of x and g of x, and it's asking us to add those together. So what you're going to do is you're simply going to add those two functions together. So you're going to start by writing out the f of x function, and you're going to be adding that to the g of x function. And since it's addition, you don't have to worry about any order of operations or anything like that. Now we can just go ahead and combine like terms. So I combined the x's and then the constants, and I get x squared plus 8x minus 4. Now over here I'm going to have to subtract them. So when you do subtraction, you have to be a little bit more careful, because if I'm subtracting this function away from this other function, I'm subtracting the whole entire thing away. So I need to make sure I put parentheses around that to indicate that I'm subtracting each and every term inside that parenthesis. Okay, so you can't just say subtraction, because then you wouldn't be properly subtracting the two. Your order of operations would be wrong. Your distribution would be wrong. So just be careful of that. So I'm going to have to distribute a negative here. That's going to give me x squared plus 5x minus 2 minus 3x plus 2. And then I just combine like terms. And what's going to happen with the 2's? Cancel out. Very good. So that's the difference between addition and subtraction. I will say one of the number one mistakes I see in general across the board in all my classes I teach is people not distributing the negative. So don't be one of those people. Distribute your negative. All right. So next one. Next one is multiplication. So if we're trying to multiply these two equations together, the easiest way to do that, since one is a trinomial and one's a binomial, is to use the box method. So I'm going to draw my box out. And the number of boxes I need is going to be based on the number of terms I have. Since I have 3 terms multiplied by 2 terms, that means I need 6 boxes. So that's going to be x squared plus, or sorry, it's a minus, minus 7x plus 2x, and then x plus 4. I'm going to multiply these corners together. Negative 28x plus 2x plus 8. And then you're just going to combine the like terms. We have x cubed minus 3x squared plus, or minus 26x plus 8 is what I got. Just verify that. And then that would be our final answer because there's nothing else I can combine because there are no other like terms. So for the next one, it wants us to take f of x and divide it by g of x. So I'm going to write it out as a fraction first and foremost. And then from here, I want to see if there's anything I can do to go a little further with it. In this case, the numerator doesn't factor, so I can't like try to cancel anything out. However, I can do division because the degree of the denominator is lower than the degree of the numerator, which means I can divide. So we have the option of using synthetic or long division. I opt to use synthetic when possible. Is it possible in this scenario? Yes, because this is a linear binomial with a coefficient of 1. That means just an x plus or minus something. Fancier way of saying that. So I'm going to go ahead and use synthetic division. But yes, long division would also work here as well. So what's going to go on the outside of my synthetic division bars? Good. Inside?
1, -7 and 2.
Good. We don't have any placeholders to worry about, so I can start by bringing down my 1, multiplying, combining, multiplying, and then combining. Remember, the one next to your remainder is your constant, and then it goes up a degree every time with x. So it's going to be x minus 11 plus 46 over
x plus 4.
Good, your original divisor. And that would be the final answer. That's as much as you can do with that. So does anyone have any questions about that part? Okay, you see in this class a lot, in a lot of math classes, things never really go away. Okay, you're still gonna, everything you learn is still gonna be kind of applied later on throughout the course. Alright, so transformations of functions. We're gonna start by doing all of the vertical transformations first. Those are the easier ones. And these are the ones that we use more frequently, yes.
Is that probably the first page? Is that where there are all these different pictures?
What?
Oh, I see what you're saying. I don't remember how yours are broken up. I'll label each section though, so like these two are vertical and then,
Okay.
yeah, I don't remember how it's broken up on yours, sorry. I'll label each one though, so you know. Anything with an H or a B is horizontal, if that helps. Alright, so, this one is when we add a number to a function. So when we add a number to a function, how does that affect the function?
Moves it up.
Moves it up. So your y value goes upward. Okay? So this is what we call a vertical shift in the upward direction. So of course we're just going to draw a sketch of this as well. So you're going to draw the function being shifted upward, however many units, k units. We don't know how many because we're just talking about it in terms of, k. The main thing you need to remember about this is it doesn't change the shape or the size or the compression or anything like that of the function. It stays exactly the same. It's like a translation in geometry. It just shifts it up. It's a geometry word, rigid motion, isometry, yeah. So, next one here is going to be a vertical shift downward. So I know we did these in the beginning of the year as well, so it might be a little bit of a refresher. I'm trying to draw it in a way that doesn't look like it's changing it, but it's hard because I'm just eyeballing it, but just you get the idea. It doesn't change it, it just shifts it. Any questions about that? Okay. Now these transformations, these two are also vertical. So this one is what we call a vertical stretch. Very good. We take our our y, and we multiply it by some value. So it's always a vertical stretch if the absolute value of the number that you're multiplying y by is greater than 1. That means it's stretching it. If it's less than 1, that means it's compressing it. So this is what we call a vertical stretch. And this occurs when the absolute value of a is greater than 1. So that means that it actually makes your function more stretched out in the vertical direction. So if you were to stretch it this way, okay, that's how it's affecting the graph. So I do have a little Desmos thing I can kind of show you guys. That one's not the one we want to look at. On Desmos, this is what it would look like. This is the quadratic. You can add a slider, and if a is greater than 1, see how it stretches it out vertically? But if a is somewhere between 0 and 1, it compresses it. So that's the next one we're going to look at. So this one here is when your a value is, or whatever this item that you're multiplying, coefficient that you're multiplying y by is smaller than 1, absolute value smaller than 1. That is a vertical compression. So that gets it, stretches it it basically squishes it this way, okay, vertically. And that happens when that fraction, the absolute value of that fraction, is between 0 and 1. So what's like a number that's between 0 and 1?
0.5.
Yeah, 0.5, a third, a fourth, anything like that. Now, here's where people get tripped up. Would 7/4 be a compression or a stretch?
Stretch.
Good. Okay, you guys are smart. You got it. All right. Anyone have any questions about that? All right. So this one here is another vertical. Anyone know what this one's going to be?
A downward, like a, what's it called, a reflection?
Very good, a reflection. So this is where you take all the y's and you basically make them the opposite sign. So if they were negative, they become positive, vice versa. So this is what we call a vertical reflection. And if your function isn't shifted up or down at all, it's going to be over what axis?
X.
Good, over the x-axis. So it's as if I were to flip it down here. So everything about it stays the same. It's another rigid motion from geometry, meaning nothing about the shape or size or stretch of it changes. And if we want to really think about geometry here, vertical stretches and compressions are not like dilations either, because they don't maintain the size and shape, or the shape rather even, or the dimensions. Yes?
Do we have to like memorize all of these?
I'll explain. So the vertical, you don't have to like necessarily memorize it, but I would give you a question where I'd say like what has happened to it, and you have to know like based on the picture which one's happened. Like if I said x squared plus 4, you would know that that was shifted up 4 units.
Okay.
That would be like the kind of question I would ask. So here's where we start the horizontal ones. These are the 2 horizontal ones that are really important that you're going to see. The other ones we'll talk about. You need to know they exist. You need to understand them to this extent, but you're not going to really apply them very frequently. Maybe occasionally, but they are more advanced. So the thing about horizontal that's confusing as opposed to vertical is everything's the opposite, okay? So in this case, what do you think is happening here? It's a horizontal shift to the
right.
Yes, good. So it actually takes x and adds an h to it. So it's always going to be the opposite of what you expect. That's why horizontal can be tricky. So that's actually moving it to the right. And there is a reason for that. I can kind of explain at the end. I don't want to like overwhelm you right now. So what do you think this one's going to be?
Horizontal shift to the left.
Good.
Good job.
Good. So we're going to go left. So I will like briefly explain this reasoning. It may or may not kind of resonate with you. If it doesn't, that's okay. If I had say let's see a really simple function like x minus 4, or an expression, because it's not a function because it's not equal to anything. If I wanted to find where it crossed the x-axis, I would set it equal to 0, and I would solve for x, and I would get x equals every time I do this, essentially, what do you notice happens to the sign?
Changes.
Yeah, that's essentially what's happening with the horizontal shifts in the functions, okay? To actually find where it's going, you set it equal to 0. So that's like the reasoning behind why it's opposite. So remember, these are more horizontal. And remember, everything's opposite day in the world of horizontal transformations. So if I were to technically multiply x by something, it's really like dividing, which is like multiplying by the reciprocal of it, okay, 1 over b. And I say reciprocal instead of division because if it's not something like, if the number already was a fraction, it would be a flipped fraction, right? So I don't want to say it's always division because that kind of could be confusing. So this is a horizontal compression. So a horizontal compression is going to make it taller, right? Because you're compressing it this way. Very good. So horizontal compression,
What's the opposite?
you're squishing it this way, right?
So it's like a
So it's like a vertical stretch.
Yeah, it's like a vertical stretch, exactly. And then what do you think this one's going to be?
Horizontal stretch. B times x.
Good, b times x. This is horizontal stretch. So that's going to be wider because you're stretching it the wide way. Now, yes, horizontal compression is like vertical stretch. Horizontal stretch is like vertical compression. They are like opposites of each other. But I do want to just preface this real quick that they are not opposite identical. And I want to explain what I mean by that. And then I'll be done with it because I don't want to confuse anybody too much. Okay, so let's say we have the standard parent function x squared, okay? Now, if I said y equals a times x squared, that a is going to act as a vertical stretch if I make the a bigger than 1, right? If I make it 2. I wish they'd put this in a different color. Hang on, let me change it. It's confusing when they make them the same color. There we go. So, does everybody see how the red is a vertical stretch? Okay, so bear with me. This would be what a horizontal compression looks like if it were this. Do you see how the b is inside of the actual power as well? That's what makes it horizontal versus vertical. Vertical happens on the outskirts of the function. Horizontal happens inside the function by the x. So if I make this slider b and I make b 2 also, do these two types of stretches or compressions look the same to you?
No, because it's square.
No, because, yeah, exactly. So this one is squaring only what's happening to the x and then multiplying it by something. You see that? This one is multiplying them first and then squaring them. So while they both are types of stretches or compressions in their own way, this one happens at a different rate than this one because it also squares the coefficient. Does that kind of make sense, what I'm saying?
Mm-hmm.
It's okay if it doesn't make that much sense. This is a little bit more advanced stuff. All right, so I'll go ahead and hand out your homework. Like I said, the verticals are more important, and then these two horizontals are the oh, wait, did I forget about one?
Yeah.
Oh, I'm so sorry. Okay, I got too ahead of myself on that. What do you guys think this one's going to be?
Horizontal reflection.
Good, horizontal reflection.
Kaden, you're so smart.
So this takes x, flips its sign, and over what axis do you think this is?
Why?
Good. Will this change this graph at all if I were to reflect it?
No.
No.
No, we'll change some graphs, just not this one, right?
Wait.
If it were a graph like this and I were to do it, would it affect it?
Yes.
Yeah, sometimes it does, but if the graph is symmetric over the y to begin with, it won't affect it. Any questions? Okay, cool. I'll hand out your homework.